So we're now in a very exciting situation. The Gauss-Jordan algorithm will take any matrix and reduce it to a reduced row echelon form matrix. So here we have an example of this. I have a 4 by 5 matrix, and I plugged it into the Gauss-Jordan algorithm, and then the algorithm spit out a reduced row echelon form matrix. We have a way to we have a language that we use to talk about reduced row echelon form matrices. So remember, the pivot columns of a reduced row echelon form matrix are the columns where the pivots are. Well, what do we call the pivot columns of a general matrix? Well, the pivot columns of a general matrix are where the pivots end up in the reduced row echelon form. So in our example here, once we row reduce the matrix, the pivots are in the 1, 3, and 5 columns. So that means that the pivot columns of the original matrix are the first, third, and fifth columns. So the first, third, and fifth columns of this particular matrix are the pivot columns. What are the non-pivot columns? Well, that's the other columns. So in this case, the second and fourth columns end up in non-pivot columns once we row reduce, which means that these are the non-pivot columns of our general matrix. And of course, we use this terminology to define the rank. The rank is the number of pivot columns. So in our example here, the number of pivot columns was 3, which tells us that the rank of our matrix is equal to 3. On the other hand, the nullity is the number of non-pivot columns. And in this case, the nullity was 2. So, or the number of non-pivot columns was 2. So the nullity is equal to 2. So we now have concepts of rank and nullity that apply not just to reduced matrices, but to any matrix via the Gauss-Jordan algorithm. Okay, so now I'd like to explicitly state some theorems about rank and nullity. Our first theorem is the rank-nullity theorem. Remember, all this says is that if you add the rank to the nullity, you get the number of columns of the matrix. This makes sense because when we row reduce, every column will either end up being a pivot column or a non-pivot column. The number of pivot columns is the rank, and the number of non-pivot columns is the nullity. In particular, if our matrix is m by n, then the rank plus the nullity equals n. Another remarkable theorem is what I like to call the rank transpose theorem. What this says is that the rank of any matrix is always the same as the rank of its transpose. And this is not obvious, nor should it seem obvious. And so think about what we're saying here. What we're saying is that when we row reduce A, we get the same number of pivots as we would have gotten if we row reduced A transpose. So that turns out to always be true. Also, we have what I like to call the rank Gramian theorem. Remember that the Gramian of a matrix is the transpose of that matrix multiplied by the matrix itself. And this will turn out to be an extremely interesting matrix for us as we proceed in the course. And for example, one interesting thing we can say about the Gramian of any matrix is that it's an n by n symmetric matrix. But it turns out that it has, there's more we can say. It turns out that the rank of any matrix is the same as the rank of its Gramian. So I like to represent the first two of these theorems with a picture. So remember, the rank plus the nullity equals the number of columns. Well, we can think of an m by n matrix as a process that accepts n inputs and has m outputs. Well, I like to remind myself of the rank nullity theorem by drawing boxes over here on the left where rank and nullity are in the two boxes next to Rn, because the rank plus the nullity is equal to n. On the other side, remember, if we transposed A, the number of columns would be m, so the rank of the transpose plus the nullity of the transpose would be m, the number of columns. But the rank transpose theorem says that the rank of the transpose is the same as the rank of A. So we can interpret the right-hand side with boxes saying rank plus the nullity of the transpose equals the number of rows. So I like this picture a lot, and as we see as the course progresses, this picture will turn out to be useful in other contexts. So let's look at an example. Let's say that we are studying an 8 by 13 matrix, And let's say that we happen to know that the nullity equals 6. Well, let's look at our figure and see if we can't say anything else about the matrix. So in our figure, remember, we have boxes where we're labeling rank and nullity right next to r to the number of columns, which in this case is 13. And then we have rank and the nullity of the transpose to the right here, right under r to the number of rows, which in this case is 8. And the reason for this setup, again, is because the rank plus the nullity equals the number of columns, and the rank plus the nullity of the transpose equals the number of rows. Well, all we're told here is the size of the matrix and the nullity, but we can use these theorems to fill in the blanks here. Since the nullity plus the rank equals 13, well, we can figure out the rank ourselves. What plus 6 equals 13? Well, that's equal to 7. So now I know that the rank is equal to 7, and I can move over here and fill in 7 for the rank. What's the nullity of the transpose? Well, the rank plus the nullity of the transpose has to equal 8, so the nullity of the transpose has to equal 1. So by knowing one of these numbers in our boxes and knowing the size of the matrix, we know all of the other numbers. Also, if you think of the rank Gramian theorem, remember that the Gramian of a matrix is n by n, where n is the number of columns. So for this matrix, since we are 8 by 13, we know that the Gramian would be 13 by 13. We also know that the rank of the matrix is the same as the rank of the Gramian. So the rank of A transpose A happens to equal 7 because we know that the rank of this matrix equals 7. So this is just a small example to illustrate how powerful our theorems are. You only need a minimal amount of information to be able to say a lot about these particular objects. We also have some descriptors that we use in colloquial conversation as mathematicians. So the first colloquialism is the term full column rank. When we say that a matrix is full column rank, what we mean is that the rank equals the number of columns. There's also the term full row rank. Well, full row rank means that the rank is equal to the number of rows. When we just say that a matrix has full rank, we mean that it either has full row rank, so either the rank equals the number of rows, or it has full column rank, meaning that the rank equals the number of columns. We say that a matrix is rank deficient if it is not full rank, meaning that the rank is less than the number of rows, and the rank is less than the number of columns. One of the most important terms in linear algebra is the notion of non-singularity. We say that a matrix is non-singular if it is square, meaning the number of rows equals the number of columns, and it is full rank, meaning that the rank equals the number of columns, which again happens to equal the number of rows. So a square matrix that has full rank is called non-singular. And singular is the opposite. So singular means that we're still square, but we don't have full rank. So the rank is less than the number of rows, which equals the number of columns. So here I have an example where somebody has taken 4 matrices and row reduced them for us. So someone reduced a matrix A to produce this reduced row echelon form. Someone row reduced B to produce this one, reduce C to get this one, and reduce D to get this one. I have our table, a table organizing all of the descriptors from the previous slides. And so we can quickly check, given this information, which descriptor applies to which matrix. So which of these matrices has full column rank? Well, full column rank means that the rank equals the number of columns. Well, for A, the number of columns is 3, but the rank is 2, so that's out. For B, the number of columns is 3, but the rank is 2, that's also out. For C, the rank is 3, and the number of columns is 3, so C is full column rank. And D has rank 1 with 2 columns, so it is not full column rank. A similar analysis applies to the term full row rank. Of these matrices, the only one that has full row rank, meaning that the rank equals the number of rows, is, I guess, matrix A and matrix C. What about full rank? Full rank means the rank either equals the number of rows or it equals the number of columns. The only matrices that satisfy this requirement are A, which is full row rank, and C, which happens to be both full row and full column rank. What about rank deficient? Rank deficient is the opposite of full rank. So if you say that a matrix is rank deficient, what you're saying is that the rank is less than the number of rows and less than the number of columns. Well, for B, this matrix B is the matrix B is 3 by 3, and the rank is 2, so that's rank deficient. And for D, that matrix is 3 by 2, and the rank is 1, so that's rank deficient. What about the term non-singular? Non-singular is a descriptor that applies to a square matrix that is full rank. Of these four matrices, only B and C would be square, but B has rank 2 even though it's 3 by 3, and C is rank 3 and 3 by 3. So C is non-singular, and the only singular matrix here, so remember singular means square and the rank is less than the number of columns. Well, again, B and C are the only square matrices, so those are the only potential options here. But C is non-singular because it has full rank, and B has rank 2 even though it's 3 by 3, so B is our only singular matrix. So it's useful to acquaint yourself with this language because this is how mathematicians often talk about matrices. Perhaps, like maybe the property of rank and nullity in reduced row echelon form that will prove most useful, or that we'll keep coming back to, is the column relations. So remember, if you give me a matrix that's in reduced row echelon form, I can easily write down the column relations. So here I have a matrix in reduced row echelon form. The pivots are in the 1, 1, and 2, 3 positions. And we get column relations by studying the non-pivot columns. The first non-pivot column is the second column, and our column relation here says the second column is 3 times the first column. For the second non-pivot column, that's the fourth column, and the column relation here says this fourth column is -2 times the first column plus 5 times the third column. So we can write those relationships down. The second column is 3 times the first, and the fourth column is -2 times the first plus 5 times the third. What's really cool about reduced row echelon form is that so we can easily read off the column relations of the reduced form, but it turns out that the original matrix has the same column relations. They're just not as obvious to see. So if we look at the original matrix here, well, the first non-pivot column is the second column of the matrix, and the relationship in the reduced form was column 2 is 3 times column 1. Well, what we're finding here is that that's exactly represented. If you scale each entry in the first column by 3, you get the second column. This also applies to the fourth column. In the reduced form, the fourth column is -2 times the first column plus 5 times the third. That's exactly what's happening in the original matrix. -4, -14, 33 as a vector is -2 times the first column, 2, -3, 1, plus 5 times the third column, 0, -4, 7. So the idea is that it's easy to look up the column relations of the reduced form because of all the conveniently placed zeros. And then if we know those relations, we know the relations between the columns of the original matrix, which is originally a difficult problem.